Okay, thank you, Baher, and thank you, Roger. This is great. Um, I think we're going to move right into the final session of the day, which is on innovations in freight, logistics, and air quality modeling. We're really happy to say that we have four excellent presenters for this session, which include two on more freight and logistics innovations that have been sort of developed through CATS and the University of Toronto ecosystem. And then another two presenters that are going to be focusing a little bit more on emissions and air quality. So that's great. I think took a quick look and I saw that at least our first two presenters are ready to go. Um, so Alia, maybe you could show yourself. There you are. Okay, I wanted your face up while I gave you an introduction. Alia Galal is a PhD student at the University of Toronto, and her research is multidisciplinary. It includes urban freight transportation, human factors, driver training, and traffic safety. And so she's been doing work under my supervision for the last 4 years as a PhD student, as well as working with Professor Birsen Donmez from Mechanical and Industrial Engineering, who is a specialist in human factors. So Alia's research focuses specifically on assessing and improving drivers' hazard anticipation skills with the larger aim of enhancing safety of interactions between trucks and vulnerable road users, pedestrians and cyclists in urban areas. And Alia, I think you're due for 15 minutes, and then we'll have another 5 minutes reserved for questions. Before we move on to the next presenter, I'll hand the floor over to Alia.
All right, thanks, Professor Matt. Hi, everyone. My name is Alia, and I'll be presenting a main piece of my PhD dissertation. And the topic or the title for my presentation is Truck Driver Hazard Anticipation Training. So I'll be mainly focusing on a simulator study that I am still analyzing or conducting. So the big question before I start my presentation is what is hazard anticipation and why I am actually focusing on hazard anticipation. So hazard anticipation consists mainly of four steps. So first, it's the awareness of any traffic risks and any threats to safety. Second is to conduct a thorough visual search to detect any elements that might contribute to unsafe situations or unsafe scenarios. Third, it's to predict what could happen or when and where hazards can materialize on the road. And last but not least, for sure, it's to respond in an appropriate and timely manner to avoid any hazards from materializing or collisions or unsafe situations to happen. Unfortunately, hazard anticipation skills are a bit underdeveloped in young and novice drivers. So hazard anticipation is a skill that gets better with experience. Unfortunately, also, it has a big effect on collisions and safety. So many collisions can be attributed to lack of hazard anticipation. The good thing, though, is that hazard anticipation can be trained. So we have seen, or literature has seen, a lot of improvement in hazard anticipation skills after training. So this is a picture that shows that if a driver has good hazard anticipation skills and we have a truck parked on the right side of the road and the driver or the ego driver is approaching the blue rectangle on the road, someone with good hazard anticipation skills would predict that the red circle might be an area of interest or might be an area where a possible hazard can materialize. So we see a crosswalk right behind the parked truck. So the view can be blocked, and behind that truck might be like a pedestrian or a cyclist that is intending to cross the street. So looking at literature, many research has many researchers have found that the main reasons for truck collisions are related to driver recognition and decision errors. And for novice drivers specifically, they have been found to have difficulties specifically in identifying areas of interest or areas where possible hazards can happen, or where hidden risks could emerge. The good thing, though, is that hazard anticipation training was proven to reduce collisions and improve driver behavior. So many studies have been conducted on the effectiveness of hazard anticipation training, especially in passenger vehicle drivers, not specifically for truck drivers. And we have seen a lot of improvement after training in terms of glance behavior, speed choices of drivers, vehicle maneuvers, and the detection and response time to hazards. Also in real world, many countries have used hazard anticipation lessons and hazard anticipation tests as part of their licensing procedures. And those countries are, for example, the UK, Australia, and Netherlands. And the results after applying this specific module were favorable. What's unfortunate, though, is that we have not identified any studies in literature that have examined the effect of truck driver hazard anticipation training on safety. So with my research, I'm trying to bridge that gap with those two objectives in mind. So first, I developed a truck driver hazard anticipation training module. And my second, or main second objective, is to test the effectiveness of this hazard anticipation training module on novice truck drivers. And to realize those objectives, or to test those objectives, we have conducted a simulator study, truck simulator study. So this is how the study design looked like. We invited novice truck drivers and truck driving trainees to come here on campus at U of T to conduct the simulator experiment. So they first conducted two pre-training drives. They then got the training, which is the hazard anticipation training. We also had a placebo training, which I'll talk about in more detail shortly. After the training, they conducted another pair of experimental drives, and finally we got all the data. We collected all the data, and we're now playing around with those data just to assess the effectiveness of the training. So we had two groups of participants: the experimental group, which received the hazard anticipation training, and we also had a control group that received the placebo training. Again, I'll talk about both types of training shortly. So each participant conducted 4 drives, so 2 pre-training and 2 post-training. So we tested a total of 8 scenarios, so each drive included 2 scenarios. For that, we used 2 pieces of equipment. First of all, the truck driving simulator. So this is how it looks like. It consists of a wide screen consisting of 3 large screens that show the view as if someone's driving on the real world. It also has a steering wheel and a driver's seat and a dashboard, and it has also a gear shifter, but for this experiment, we just used automatic transmission. The simulator is also equipped with 4 cameras that show different views of the driver, as you can see on the right-hand side of the slide. Participants or truck drivers also had to wear eye tracking glasses, so that we can capture or collect data that give us information about where they're looking and how long they're looking at areas of interest and so on. In terms of scenarios, as I mentioned, we tested 8 total scenarios. So this is one of the scenarios that we tested. On the left side of the slide, you can see the top view of the scenario. So the truck would be approaching or crossing an intersection. There would be a solid fence at the right side, which is blocking the view of a cyclist who's crossing perpendicular to the movement of the truck. I have a short video here, so I hope it works on your end. So here, that's the intersection. To the right of the road is the fence that's blocking the view of the driver. And when the driver is approaching the intersection over here, we can see like a cyclist which does not have the right of way, but still they're moving in the direction perpendicular to the movement of the truck. So a driver with good hazard anticipation skills would slow down and wait for the cyclist to cross before they can cross the intersection. This is like the view of another scenario. So it's a jaywalker that decides to cross mid-block in front of the truck. And again, good hazard anticipation skills show if the driver decides to slow down and like uses their eye to look frequently at the right side of the road. These are the remaining 6 scenarios. I don't think we do have enough time to look at each one of them into detail, but the top 3 scenarios involve intersections and turns, truck turns, and the bottom scenarios involve a lane closure and a jaywalker and children playing at the side of the road. In terms of training, so we had 2 trainings. So I'll start with the experimental training. So it was a video-based training. Participants had to watch a 15-minute video where I defined what hazards are. I provided some examples of potential hazards that happen in urban areas. I also mentioned main driver errors, how to mitigate them, and how to mitigate collisions. In the second part of the experimental training, we provided or we showed a couple of scenarios, hazardous scenarios, and the screen would freeze in the middle of the scenario, and the drivers would be asked what could happen next. So they were encouraged to think about how and where hazards might emerge. And then after that, they were given the correct answers, and they were given hints on how to avoid collisions and mitigate hazards from happening. We also had a placebo training, which half of our participants received. So it was nothing related to hazard anticipation, because that's the control group for our experiment. So it was also a video-based training that consisted of information about long-haul trucking and what everyday life of a truck driver looks like. So we ended up with 26 participants, including 4 females. All of them were either in training, so they were actually receiving truck driver training, or were novice drivers. We recruited them through the Truck Training Association of Ontario. So we contacted participants directly to invite them, and as a thank you for participation, we compensated them with $200 each after conducting the experiment. This is the age distribution of our participants. So about 70% of them were 40 years of age or below that. But we also had a bunch of them who are kind of older drivers. This is the training status, the profile of the participants in terms of their training status. So we got trainees, we got participants who finished their training about a year ago, and we got some of them were a little bit more experienced. So they had 2 to 5 years of experience, of truck driving experience specifically. Because we reached out to specific schools. So some of the participants who participated in the study had actually simulator experience before through their truck driving schools, but some of them haven't had any simulator experience. This is how the eye tracker looks like, or how the eye tracker data looks like. So the eye tracker is equipped with 3 cameras in total. Two of them point towards the pupils, and one of them points towards the road. And then the software that we use overlays both views together so that at the end we know where exactly the driver was looking at all instances. And through this software and through this piece of equipment, we can analyze glance durations, glance frequencies towards areas of interest. We can also measure the scanning patterns of drivers in terms of mirrors, where and when they look at mirrors, how frequently and for how long, the percentage of eye closure, and many other variables. The truck simulator also collects a bunch of data, so we can get up to or more than 150 variables through the simulator, but the ones we are more interested in are the time to collision, how fast and how strong the drivers press on the brake and accelerator pedals, what speeds they drive at, their lane positions, especially when approaching areas of interest or areas where hazards can materialize, their steering wheel positions, their headways, and many different other variables. So we have completed the data collection. We are currently in the data analysis phase of this project, but we do have some expected results and some preliminary results. So we expect that a hazard anticipation trained driver identify and recognize potential hazards earlier and better than non-hazard anticipation trained drivers. We also anticipate, and we have actually seen that drivers who receive the training do more frequent and wider scanning of their environment, so they're more aware about what's going on around them. So this also gives us a hint that they're more prone to react in a proper manner. They also perform longer and more frequent glances towards areas of interest and towards hazard cues. They reduce their speeds when approaching potentially hazardous spaces or places, and they overall drive more safe. So to sum up, truck driver hazard anticipation training is not a point of focus, at least in Ontario. And for that reason, we have developed our own hazard anticipation training module for truck drivers with a focus on pedestrians and cyclists. We have conducted a simulator study with 26 participants to test or to assess the effectiveness of that hazard anticipation training module. The participant behavior was measured using different kinds of equipment before and after training. And we expect, but we are very confident that training is an effective way to increase vulnerable road user safety, especially when given to truck drivers. With that, I conclude my presentation, and I'm looking forward to hearing any questions or feedback. Thank you.
Wonderful. Thank you so much, Alia. Excellent presentation. I'd now like to open up the floor for questions. Maybe if you're going to ask a question, you can either put it into the chat or you can flip on your video and just ask Alia directly. So lots of opportunity for questions. Maybe while we're waiting for people to work up the courage, I will ask Alia what the effects that you're measuring in your simulator study seem to be quite immediate effects. And I'm interested to know what you know about how long truck drivers would retain the sort of the knowledge and experience gathered through the training.
So as I mentioned in the earlier slides in my presentation, hazard anticipation skills get better with experience. So the more experience you gain, the better your hazard anticipation skills get as a driver. So we would have loved to test drivers' hazard anticipation skills over a longer period of time. So a bit later than on the day they received the training, but that wasn't very feasible given like the very hard and very difficult recruitment of truck drivers because they're considered professional drivers and they were very hard to approach and to reach. But yeah, so I guess that um, measuring the effect of this kind of training on the long term would be a great research question.
I guess it would make for a long PhD as well. I see that David, I'm not sure what David's last name is, has asked in the chat, have you taken this training to the insurance industry to find out if they would give a discount for drivers who take the training?
I have not done that, but the training was actually constructed with a lot of input from the industry. So we have consulted a lot of industry professionals during the development phases of our training. I know that um, this actually, so I know that TD Insurance has their own um, like way of tracking how safe drivers drive, and they get compensated or their insurance gets reduced the safer they drive. But I'm not aware of anything that about that in terms of truck drivers.
Thank you. Does anybody else have a question for Alia? Bahar Abdulhai.
Yes, thanks, Ali. It's kind of shot in the dark. Do you think your simulation platform could work for testing autonomous driving for trucks? So instead of the driver sitting in the seat and making decisions, you have an algorithm running the car. And you know from, for instance, the detection method it uses, what is it looking at and what not, and how to improve the autonomous driving based on that.
Yeah, so I think the simulator that we have also works with automated driving, and so for our passenger vehicle simulator, we do conduct studies on automated driving. So like take over timings and when the driver perceives a situation to be hazardous while the vehicle is autonomously driven. So such kind of research is being conducted on the passenger vehicle simulator, and I believe it's also possible to do it on the truck simulator.
Okay, it would be interesting to see if it is safer.
Yeah.
Yeah, thank you.
Excellent. Well, in order to keep on schedule and to finish our session on time this afternoon, so we can all go watch the results of the American election, I'd like to thank Alia for her excellent presentation, and we'll move on to our next presenter. Next presenter is Hassam Rashidi, and he's going to be presenting a learning framework for generating practical last mile delivery routes. Hassam is a PhD student in transportation engineering at the University of Toronto, working under, well, my supervision, as well as his co-supervisor, who is Professor Mehdi Nourinejad from York University. Hassam's research is focusing on treating algorithmic biases in the supply chain, looking at combinatorial optimization and tactical planning for last mile deliveries. He started his PhD, before he started his PhD, he did his bachelor's in civil and environmental engineering from Sharif University of Technology. And this is new to me, when he's not working on his research, well, I knew about the stargazing. He's a stargazer and an amateur, maybe semi-amateur, semi-professional stargazer. I know that, but I didn't know that he practices martial arts. So he'll be ready for your questions. With that, I'm going to pass the floor over to Hassam. Go ahead, Hassam.
Thank you, Professor Rhoda, for the bio. And yes, I've started martial arts recently. And I just wanted to make sure that if you could confirm that my slides are shared, that would be awesome.
Yes.
All right, thanks. So good afternoon, everyone, and thank you for attending this session. I'll be presenting my research paper and my thesis about machine learning and combining machine learning with operations research to consider driver preferences in last mile routing. So last mile deliveries refer to the final leg of the supply chain where you have a depot and a truck located at the depot basically transports some packages or parcels to the consumers. And we usually formulate this as a traveling salesman problem, which is an optimization algorithm that generates the optimal sequence that would minimize the total travel time for the truck or minimizes the emissions or whatever objective function that we may have. So this problem has existed for the last 50 years, and a lot of companies, retailers use it. But something that we recently noticed is that these algorithms, they really push for minimizing costs for the retailer or making deliveries faster, and they don't really consider the experiences or the preferences of the drivers. And that leads to the drivers deviating up to 75% of the time from the optimal sequence that we impose on them or ask them to follow. So, for instance, we have a delivery instance for Amazon delivery. Let's say each node here is a consumer where they have some packages that they requested for delivery. If we optimize this route or the visit sequence for this instance, we're going to get a visit order. And the color of the nodes, the consumers, represent how early in the day they were visited to. So the nodes that are white, they were visited earlier in the day, and the total travel time for this optimized tour is 7 hours and 30 minutes. However, if we look at what the drivers performed in the route, we see that these consumers were visited earlier in the day, and the other group of consumers at the end were visited actually like earlier. But we see that the total travel time between these two solutions for the same instance is only 15 minutes different. So there's a 7-hour difference in the arrival time at specific consumers at the highest value of it. And if you're expecting your delivery, let's say for 10 a.m. and when you're getting it is 5 p.m., then there's a higher chance of failed deliveries, right? So we don't really want drivers to not be considered in routing. Well, first of all, for their personal welfare and their preferences, and second, because it indirectly affects the quality of the service and also efficiency. So in the past, before there was this much of a demand for last mile deliveries, the literature or the best algorithm that we had basically said, let's say we have a depot and we have the service region, let's divide the service region into multiple neighborhoods and just consistently dispatch the same drivers to the same neighborhoods and not give the drivers any sequences to follow. So the drivers would basically become more familiar with each neighborhood and consistently deliver to the same consumers at the specific times of day. So for instance, if a house was in the blue region here, it was always delivered to by the blue truck. And if it was placed in the red region, it was always delivered to by the red. But since the demand for last mile deliveries has exploded in recent years, maybe last 5 years, we needed more drivers and we needed more third-party logistics or couriers to help us out. So we don't always have the same dedicated drivers for the same neighborhoods. And these drivers are changing almost every month. So whenever a new driver comes into the fleet, they have to navigate the new learning curve, and that introduces some inefficiencies to the service. So our goal here is, what if we try to learn from the experienced drivers and we learn what the drivers prefer to do? So we would change our routes instead of just optimizing them for total travel time or costs. We consider these human preferred characteristics of these routes. So in this research, we're trying to increase the practicality of the delivery routes by first identifying what characteristics of a delivery route would increase its quality. And then we come up with a metric that would quantify what the expected practical performance of the delivery route would be. And we also want to we developed a AI-based algorithm to help us generate these routes in a reasonable manner, which is fast and scalable. So just to give you an overview of our framework, our framework basically takes some historical data into account. And let's say these historical routes basically have been ranked by a logistics planner based on whatever KPI the retailer may have, and sorted such that some routes are high quality, some are medium, and some are low. We extract some characteristics from each route type, and we train a machine learning model that would be able to determine whether a potential route for an instance would be high quality or low or medium. It would give us a probability of this. So our model basically takes this graph and it will tell us the probability of having a high practical route in the field. And we use this machine learning model in a heuristic that we designed to prescribe routes that have a higher quality and are more aligned with the preferences of the drivers, consumers, and the retailers. So we're trying to see all the needs of the stakeholders involved, and we're trying to balance that. So for the data, we were very lucky to have been able to use the Amazon Last Mile Delivery Challenge data. So this was a competition in 2021 where Amazon released over 6,000 historical instances of their deliveries that they performed in 5 cities in the US. So the Amazon logistics planners have rated these routes based on their quality, and the dimensions of interest in that was the driver experience, consumer satisfaction, and the productivity of the route. And we basically train and test our model on this data. And we make sure that we split the data in such a way that we're not training and testing in the same instances. So once we went over the data, we noticed that, yes, the quality of the route is not only related to the duration or the expected route duration, basically, and there are other components of the route that affect its quality and practicality level. So these characteristics from a high level can be divided into instance-related and route-related, and the difference between these two are basically whether they would change if the stop visiting sequence would change or not. So for instance, the number of stops for the instance would not change if we were to change the visiting sequence in the route, whereas the turning sharpness, the backtracking distance, and the visit time of a specific stop would definitely be changed. I'm going to explain these characteristics in more detail in the future slides. So starting off with backtracking distance, we noticed that drivers do not prefer backtracking, which refers to the instance where a driver has delivered to a specific neighborhood and they're asked to revisit the neighborhood again, maybe in a few hours. So they prefer to deliver every stop within the specific neighborhood once and then never return to that in the same day. So how do we quantify that? We tessellate the service region into hexagons or zones or cells, and we make sure, and if a driver is asked to deliver to a hexagon or a cell that has been previously to, we count that as a backtracking. The next characteristic that we noticed was influential on the quality of the route was the turning sharpness. We noticed that drivers don't really like making very sharp turns, and high quality routes basically rather deliver orders in a straight line and then move on to the other streets, because probably this would introduce less left turns for the driver or the route, and it would probably save them more time. And after that, in the data set, we had some information about the time of visit for a specific consumer, and we were able to extract some information that we called quality associated with the time of visit. So let's say neighborhood A or cell A, we want to visit it between 9 and 10 a.m. Based on the historical data, we know how many of the visits between 9 and 10 a.m. to this specific neighborhood was part of the high quality routes and how many of them were part of the low or medium quality routes. So let's say between 9 and 10, we've visited this specific neighborhood 15 times, out of which 5 were high quality, 10 were low quality. In addition to that, we have some information about the success of the delivery handoff. So out of the 31 packages or deliveries attempted in this specific duration, 28 of which were successful and 3 were not successful. So we extracted this information and we developed a new independent variable that we use in the machine learning model. I'm not going to get into the details of it, but we basically use this information as well in our AI-based model. So once we train the machine learning classifier such that we can determine whether a specific route will be practical in the field, we design the heuristic around it. So how does our heuristic work? It's a simple random insertion heuristic with the machine learning model as the cost function. So basically, we generate a route by randomly selecting a consumer and inserting it into a partial route such that the cost of that insertion is minimized. So we're just inserting consumers wherever we can minimize the number of backtracks, the total route duration, the turn sharpness, and also we want to improve the quality of the visit time to the nodes as well. So basically, the animation here shows how that works. So we randomly insert the nodes, the missing nodes into the route, and we are able to very efficiently create a route that would be feasible and improve the quality or the practicality of the sequence that we prescribe to the drivers. Once we did that, we tested our algorithms on the Amazon data set, and compared to the benchmark that were available to us, we were able to generate 24% more high quality routes, and that's 24% more than the courier performed. So the routes that the drivers performed, they were ranked by the Amazon logistics planners, and 44% of them were high quality, and 55% of the routes that the drivers performed were low quality. Our model is believed to have 68% high quality routes, and we rank these based on our model, and we take care of the incorrectness of some of the outputs of our model, and we correct these values. So these values could be compared to the courier performed routes, and on average, since we're adding more things into the optimization function, we are sacrificing the route durations by 20%, and we're getting 24% more high quality routes. And compared to the benchmark on this data set and research question, our model performs the best. And just to conclude and wrap up and provide a summary, so we designed a solution generation strategy to enhance the quality of the routes. Our method is data-driven and scalable. We consider driver experience, customer satisfaction, and productivity in our optimization. Any other KPI could be also considered if wanted to. And we are able to create 24% more high quality routes compared to the courier performed. And this comes with a modest sacrifice to travel time, which is around 20%. And with that, I would like to conclude my presentation, and I'll be more than happy to answer any questions that there may be.
Wonderful. Thank you, Hassam, for the excellent presentation. We'd like to invite comments or questions from our audience. All right. Well, I'll take the opportunity to ask a question, Hassam. I know I've asked you many questions about this project before in the past, but just for the sake of sparking some conversation, I'm interested to know how good drivers actually are at finding routes that outperform the routes that an algorithm might say is the shorter distance or the shorter travel time. Like in your experience looking at the data, do you think drivers really can outperform the best performing algorithm?
That's a great question. So from the literature, yes, there's a lot of empirical evidence that the experienced drivers are better than an algorithm in finding these routes, because they become more familiar with the region itself. They have access to real-time information from, let's say, Waze or Google Maps, and that really helps them in deciding their next visiting stop. But at the same time, the data set from Amazon did not disclose the observed travel time of the drivers. So there was no way of determining what proportion of the drivers were able to outperform the algorithm from Amazon. But they do say that we consider those drivers or the experience of the drivers in the labels that they have created in the data set.
I'm looking for other questions, but maybe I'll just ask this then. As our algorithms get smart and take advantage of the experience of drivers, can they, do you think, in essence, that ingestion of information from so many experienced drivers could be built into the algorithms and eventually make drivers' experience less important?
That is also an interesting question. So personally, I don't think that would ever happen because the transportation network is very random. It changes very dynamically. So you would always have the drivers, you would always need the drivers to really experience the smaller points in the field and see, yes, this algorithm doesn't work because there's a road closure or whatever reason. At the same time, holding on to these historical routes is very costly because they require hardware or like a disk to be stored on, and that's quite expensive. So they have to be renewed every once in a while. And there is some research on this, on how to retain or hold on to these historical routes if there's an optimal way of doing it. But just to answer your question, I think no, the experience of the drivers will not be obsolete or go lesser in value in the future.
Great. I'm glad you have such confidence in the human brain as a participant in the future. So that's excellent. Not seeing any more questions, so maybe I will thank Hassam for an excellent presentation, and we'll move on in our agenda. Thank you, Hassam.
Thanks.
Next up, we have Milad Saidi. And Milad, so we're shifting now from the freight transportation component of the session over to the transportation emissions and air quality component. Milad Saidi is going to be presenting spatial prediction of traffic-related air pollution using mobile sensors. And let me give you a brief bio for Milad. He's a PhD student in civil and mineral engineering at University of Toronto, working with Professor Marianne Hatsopoulou. Milad's research focuses on air pollution modeling and understanding the impact of traffic on air quality. And outside of his research, he enjoys exploring the city and staying active, playing soccer, and then occasionally having surgery to recover from his soccer injuries.
Yeah.
And is what you're having now. So since you're not playing soccer, why not give us a presentation
Okay, thank you.
on prediction of traffic
Thanks
related?
for the introduction. But yeah, I have started swimming. Swimming might be better. Okay. Can you see my slides?
Yes, that's perfect. Thank you.
Okay. So yeah, as Matt mentioned, I'm like a fourth-year PhD student working on a special prediction of traffic-related air pollution using mobile sensors. So in the first slide, I'm going to explain how this research is relevant to this event. As I mentioned, the focus of research is on a special prediction of traffic-related air pollution in urban setting using mobile sensor. So as we know, traffic is a main source of air pollution in cities, and it impacts human health and quality of life, especially in denser area. So the objective of this research is to develop predictive models to identify highly polluted area of the city and how they are linked to different kind of like vehicles. And in this way, we can help policymakers to like come up with better policies. Like, for example, in this picture, we can see like by using vegetation barriers, like along a highway that has higher concentration, policymakers can like come up with better interventions and policies. In order to understand the variation in air pollution, there are several ways. First one is just using like stationary stations, but the problem is that there are just a limited number of them, like, and they are costly so there are limited number of them in each city, and they are costly, so they don't give us like a good special coverage to give us understanding of like how the special surface of air pollution is changing in different location of the city. Also, we can use like dispersion models. These models are highly computationally costly, and they are less precise. Or we can use like chemical transport models. These models also are like for larger scales, and they consider like interactions, like chemical interactions and all the interactions that happens in atmosphere, but they have a coarse resolution. And at the end, we have like land use regression models, which is my focus. They are better for urban setting because they kind of capture localized pattern. So we can see how like pattern across different road, different places, different location in the city changes. So the goal of this study is to predict a special pattern of traffic-related air pollution in urban area. By pinpointing like the highly polluted area, we can link how this highly polluted area are like linked to heavy traffic, different kind of how they are linked to different kind of vehicles. Also, we can examine these models across different like years to see how traffic has changed and how these changes has impacted the quality of air. And at the end, we want to like develop a tool to give insight to like urban planner and policymakers. So in another word, this is like the objective in a picture. So we have a mobile sensor that collect the data, collect like air quality data, concentration of pollutants. We have like installed several sensor on this like mobile sensor. And then we drive this mobile sensor across the city to capture images. We use these images to like, we use a object detection model to see how many cars are in each models, how many vehicles, different type of vehicles are in each model. And then we use land use regression model to come up with the surface. And then we use like this, like the map for the traffic, and we show how they are related to like the highly polluted area of the city. For collecting data, as I mentioned, we used Urban Scanner, which is a mobile sensor. We have installed several different sensors on them. For example, we installed like a black carbon sensor. This sensor is like recording every 10 seconds. We had ultra fine particle sensor along with several other sensors. But in this study, I was just using the data for black carbon and ultra fine particle. Also, we were like recording GPS locations, like every 1 second. Every 1 second, we have the location of the car, and we could extract like which level of pollutant is related to which part of city. Also, we were recording the 360-degree images to get the context of traffic and surrounding. We did 3 campaigns. One was in 2021, which was for 34 days. One was in summer 2023, which was 28 days. But if you remember, there was like wildfire days in 2023. And there was like, so we wanted to just capture the impact of traffic. So we excluded those days from our data because like the concentration were highly impacted by like wildfire. And also we had another campaign which was in 2024 winter. It was just for 10 days of sampling in Feb to 8th of March. This just shows the map of the routes that we used for sampling during 2021. Also, we repeated like the sampling on each route to like capture the variation across different days on those routes. So this is the structure of the image detection model that I was using. We had like pre-trained YOLO model. Then we customize it, like using transfer learning. We customize it to have like more type of vehicles in our detection. We had like 1,600 labeled images to have more categories of car, because YOLO just was detecting just car. Every single car, all the vehicles was detected as car, but we customize it to be able to detect car, bus, pickup, light commercial, single unit trucks, combination trucks, and TTCs in city of Toronto. And we had around like 400 images for each sampling campaign. It was like 200,000 for 2024 winter, and like close to 500K for 2021 and 2023. And then we detected this type of vehicles and we created a map for each of them. So for example, on these routes, we extracted the average traffic map for this route during that sampling campaign. This just shows a statistic description of the data. So as I mentioned, we had BC we recorded BC for 2021, 2023, and winter 2024. 2021 and 2023 was in summer. Also, we separated the wildfire days because we just wanted to isolate the impact of traffic on like these pollutants. And we saw that in 2021, we had higher concentration for BC. And in 2023, the concentration was less than 2021, but it was more than winter 2024. For ultrafine particle, we had data for like winter 2024 and 2023, which they were in like same kind of range. So we want to isolate the traffic impact on pollution level. In this like slide, I'm showing just the box plot for variation of pollutant across different routes. For example, in this one, this is like black carbon concentration. This box plot shows the black carbon concentration on expressway. If we compare it with the combination trucks, the level of like number of combination trucks were higher on expressway, which was resulted in higher concentration for like 20 for expressways. Same for like single unit trucks. Also, we want to especially see and normalize how they impact the quality of like air in the city. So we developed a land use regression model. We had the sampling. We extracted the like data from stationary stations, air quality data, and climate and meteorological data in a station from downtown, and we used GIS variables as input to train a model and then to predict the concentration of these pollutant across the city. This one just shows the concentration across different years. For example, for BC summer 2021, we had this surface. For BC summer 2023, we had this surface. And for BC winter 2024, we had this surface. And same for ultrafine particle. In this slide, I'm going to just show how each kind of traffic was impacting, and then we are normalizing it by extracting the correlation across different part of the city to extract how much of each pollutant has been produced by different kind of vehicles. For example, in this map, we are seeing higher concentration of pollutant on highways. If we check the number of combination trucks, we see higher number of combination trucks. We see higher number of single unit trucks on highways. Also, if we check this area, we don't have any combination trucks or single unit trucks. We have some single unit trucks, but the main cause of having higher concentration across this area was impact of light commercial trucks. So in this research, we want to kind of help the policymakers to make decision on traffic management, how they can reroute the heavy vehicles to have higher to reduce the emission and to reduce the the concentration of pollutant. We want to give suggestion for infrastructure planner, give suggestion for zoning decisions and policy support. And also we kind of want to raise kind of awareness by sharing pollution maps to promote kind of eco-friendly commuting. We also had several challenges, which was for data collection. Data was super impacted by environmental factors. They were impacted by traffic, and they had temporal variabilities. Also, we had some challenges for data integration and logistic, because we need to have a detailed planning for consistent monitoring routes. So this is just insight for what we are working on it for now, and we will add on to this research. So we want to add a special correlation analysis, how and kind of normalize how each vehicle type would impact the concentration of this pollutant. And we want to evaluate how traffic variation can have impact across different year, and how in 2021 it has changed, and how it has resulted in a change in 2023 and between summer and winter 2024. Also, for future work, we are considering testing the transferability of these models across different years. For example, if we train a model, LUR model for 2021, are we able to transfer it and use it for 2023 or not? Also, we want to add multi-model integration, because we were just using GIS variables and temporal variables from stationary stations as input for LUR models. We want to, we might it is just in the beginning of the research, so we might consider multi-models to integrate images and GIS variables to see how these images can help the model to have better output, better accuracies. Also, by doing more campaign across different urban setting, we would get better accuracies. And by sharing this result, we can kind of improve the public accessibilities, and we might be able to, it is hard, but might be able to work with policymakers to kind of help them with policies that can have good impact on people's health. Yeah. Thank you. This was my presentation, and I'm looking forward for questions.
That's excellent. Thank you, Malad. Great presentation. And I'd like to open up the floor for questions for Malad. Maybe I'll start it off. I'm interested in these driving campaigns.
Yeah,
Like there's a lot of kilometers drive for a
yeah.
lot of days. Can you just share like your experiences of like are there strategies in those campaigns for how close like clearly if you were following a heavy duty truck
Yeah.
that looked like a heavy emitter, that might sort of affect the measurements for a good stretch of the roadway just because you happen to be near one heavy emitter. What kind of strategies did you use in the campaigns to avoid that kind of bias?
Yeah, so in fact, we have this kind of bias. So one of the things we can do just by repeating the sampling across different days. This was one strategy. Also, like I'm reading some papers that's kind of use some methods to like block all these variations, across time and across location. Yeah, yeah. So yeah, we were like for sampling, we were just repeating. What we can do for improving, like removing those biases, we can, apart from sampling, we can use some strategies to block the correlate those biases. Yeah.
Great. Thank you. Any other questions from our audience? Oh, we have a bit of time. So maybe let me just ask you another one about
Yeah.
transferability. If you were to transfer this methodology
Yeah.
To a place like, for example, Calgary, take all
Okay.
the learnings from here, and what would have to be done in Calgary? Would they have to have a campaign with camera data on a vehicle, or could they just take the land use attributes from like a spatial regression model?
So if they have some sampling, it would be good because after training for like Toronto, you can use transfer learning, even if it's for like 4 days, 5 days, 10 days. It shouldn't be that much long, but if it's long, it's better in Calgary. But we should like use transfer learning. It is better to have that. If we don't have the data for that, it might be helpful to have data from different cities in Toronto and then target just Calgary, like Toronto, Montreal, Edmonton, and then use this data to kind of train the model, how like validate the model for each city. Because when we are training the model, we can use train the model for Toronto and use like somewhere else as validation. Then this model will understand will learn how to transfer. So
Do you think that it is successful in separating Toronto-based emissions from like some of the uh, air quality pollution that is arriving from other nearby cities like Buffalo or places in the United States?
just in Toronto, yeah, or regarding the transferability.
Ah,
So we should ask, are we going to transfer this model for another city, or we are just using it for Toronto? Or if we
well,
are using it for Toronto,
for Calgary, for instance, it's not very close to any other cities, really.
yeah,
So
we
there might be
cannot.
less ambient pollution from other places.
Yeah.
Do you think it would be able to successfully transfer, given that there's these, the less proximity to other major sources of pollution?
Yeah. So I'm answering to this question was two scenarios. Let's say we just have data for Toronto and we want to transfer it to Calgary. no, it's not going to happen to capture that. But let's say like we have data for Toronto, we have data for Montreal, we have data for several other cities. We use all of them like to train the models and to validate the models, and then we transfer it to Calgary. It can kind of capture, but we will not be able to do 100% good, but it will capture some like some of those effects.
Terrific.
Yeah.
Thank you very much, Malad. I'm
No
going
worries.
to move on with our program to our last presenter. And good. Arman is here. Welcome, Arman.
Thank you so much.
I'd like to introduce Arman Ganji. He is going to be presenting today an approach for traffic-related air pollution backcasting using a method which has an acronym CNN-LSTM. I hope you're going to explain to us what that means. Arman Ganji, whoops, I have to find it. Here we are. After earning his PhD in environmental science at Shiraz University, Arman became an assistant professor teaching various environmental courses, supervising research projects. And then from 2013 to 2017, Arman focused on climate modeling at the University of Quebec à Montréal, enhancing the Canadian Regional Climate Model. And then he moved on to become a senior research associate in the group with Marianne Hatsopoulou and which is the Transportation and Air Quality Research Group, same group with Malad, and is also the Climate Science for Engineering Center at the University, manager at the University of Toronto. So with that, I'm going to pass the floor on to Arman. Go ahead.
Thank you so much, Matt, for the introduction. And thank you for all of you, because it's I know that's a long day, so I really appreciate that you are still here. So the title of my presentation is Traffic-Related Air Pollution Backcasting Using Convolutional Neural Network and Long Short-Term Memory Approach. So let's start with the introduction. And in this study, we try to estimate historical traffic-related air pollution during the last 20 years. Historical air pollution level is important for those who are working in epidemiological studies and enable them to reconstruct exposure level for assessing long-term health impact. We know we can have air pollution measurement for example, for current year by sampling, but for the previous year, we need a model to estimate historical traffic-related air pollution. And we call this kind of model backcasting model. So, which is similar to the forecasting model in terms of the structure, but it has its own kind of challenge comparing to the forecast model. The first is the backcasting model must be able to estimate current pollution level for the current, no, the previous one, please. Yes, yeah, thanks. First, a backcasting model must be able to estimate the current pollution level for location where we don't have measurements, which means that we must have a special model. At the same time, backcasting model must show the trend in the air pollution based on which which we called it historical data, like traffic-related predictors, which means that this model must have the temporal capability. For this reason, this type of model must be kind of generalized model, at least in terms of the temporal variation. So, and it's a challenge for this type of model. So in summary, a backcasting model, for the backcasting model, we need a current state of predictors. We need historical traffic-related predictors, and we need a spatiotemporal backcasting model that include all these historical model. So next slide. For the current state of the model, we have the urban scanner. And we use Urban Scanner is the mobile sampling platform for sampling. Milad noted about its this Urban Scanner in his presentation. It collects pollutant pollution level, temperature, humidity, wind speed, wind direction, and traffic and build on some built environment characteristic from nearby roads. In this study, we focus on N-odor concentration. Sensor of N-odor concentration has been calibrated in the lab in isolate chamber. You can see the map of this isolated chamber on the right. And we also do the calculation with the reference station. Next slide, please. Then the sampling route to collect the sample, we had to collect. So just a moment, because it seems that my computer is going to off. Okay, it works now. Yeah. For them to collect the samples, we had some sampling route all over the Toronto. We collected sample for 30 days each year, and each day we had 75 kilometer to drive, which was randomly selected from 25 roads that you can see on the right. The time of driving was also, the day and hour also selected randomly. We have 4 campaigns in different years. 2 of them has been used to develop this model. So this part gave us the N-odor concentration or the current state of the system. Now we want to backcast these values and estimate the previous years. Next slide, please. Yep. So we need to estimate traffic-related predictor now. Some of traffic-related predictors have changed during the last year, such as traffic-related emission or annual average daily traffic. Those are our predictors, but changed during the last year for every single road that we know in the city. This means that we need to have a long-term inventory for those predictors. For this, our inventory for this study include the emission and traffic volume of volume for all the grids and road in Toronto for last 14 years. So we generated this inventory using a model, a software that we previously developed. It's called Traffic Emission Prediction Model, or we called it TEPS. Can you go to the next slide, please? TEPS use the traffic monitoring site and satellite data from different years to estimate annual average traffic count and NOx emission. It can also estimate other type of emissions as well. But for this study, we use NOx emission for every single road for all years that we have traffic count. So it used specific algorithms for each stage of this prediction, like a spatiotemporal disaggregation model for long-term traffic data, pattern recognition, regression kriging, machine learning, convolutional neural network to estimate the number of vehicles from the satellite data, and neural network to find the AAT and also emission. So we had data from 2006 to 2020. So TEPS gave us 14 years of AAT and NOx emission for all these roads in Toronto. So next slide, please. Then we have other historical variables, which are land use variables, and we assume they didn't change during the last years. The effective land use selected based on the relaxed least absolute shrinkage and selection operator that we called it relax lasso. To use the selected predictor for CNN model, we were transferring into a format similar to the image. We transferred them to the format that is very similar to the image. So we have a window with number of grid for each land use predictor, and they were overlaid on top of each other as an image channel, and then it used as an input to the model. The size of windows were determined based on the trial and error, and we checked 3 by 3 to 9 by 9 window size. Next slide, please. Here you can see the overall structure of our model. For another backcasting, we use parallel LSTM CNN model network, which integrate convolutional neural network and long-term short memory network. So in this model, LSTM and CNN network work at the same time, but in separate paths. So as shown in the left figure, the input signal include the land use build environment data from CNN. For LSTM model, we have time series data for the NOx emission, average annual daily traffic, and it comes from each single grid because we develop an inventory, a big inventory for the road. So we allocated them to the grid. Now we have a time series for each single grid in the city. So I can say that these two paths focus on different aspects. The CNN look at the spatial pattern of land use and built environment, while the LSTM capture how NOx emission and ADDT change over the time. Together, they process the input data to make accurate prediction for NO2 concentration. Next slide, please. So let's go to the result. This is the map that we collected that show collected NO2 sample all over the Trento using the urban scanner. As you can see, the level of NO2 concentration is high in the highway and downtown, near as well as near industrial part of the city. So this is the current state of the system, and we must backcast this. So next slide, please. Here we have the predicted ADT and NOx over the past 14 years that estimated using the TEPS model. And you can see ADT and NOx emission has changed over the time for the entire city. Lasso selected this variable as effective predictor for the backcasting model. We have an increase. As you can see, we have an increase in ADT and a sharp decrease in NOx emissions. So we may expect a decrease in NO2 concentration, but you will see that this is not uniform trend all over the city in the next slides. So please go to the next slide. Next slide shows the backcasted NO2 generated with CNN-LSTM model. From different years, we estimated these values. As you can see here, the level of NO2 decreased significantly over the Trento area, and we still have high values on highway and downtown in 2020. So next slide, please. On the left side, we compare the regional spatial trend of NO2 with the long-term data collected nearby road quality station. It seems that both showed similar trend in terms of decrease. But what is very important on the right side, you can see a map that shows NO2 concentration. I think we don't have the. Oh, okay, that's great. Okay, so as you can see here, we have another concentration on the right for each grid cell and the trend of each actually another concentration from 2006 to 2020. Looking at this, we can see that over the last 14 years, NO2 levels have been mostly gone down in most area based on that trend value that you can see. However, there have been some places and point that level went up. For example, along the highway, like Highway 401 and Gardiner Expressway, NO2 concentrations have gone up. This is mostly due to higher traffic in those areas. We have also seen some points increase in NO2 around the park. This area had low NO2 concentration in 2006, but by 2020, with increase in the traffic on nearby road, these NO2 levels had gone up significantly, even though they are green spaces. So next slide. To better understand how NO2 concentration change across different areas, we compare the local spatial association, we call it LISA, indicator for 2006 and 2020, as shown in this figure. The LISA map helps us to see how concentration change were grouped in a space and make it easier for us to spot pattern over two different periods. We find some interesting difference in how areas were grouped in 2006 and 2020. In 2006, high cluster, which indicated area with higher pollutant, are mainly concentrated in downtown and the northeast part of the city near Canadian Pacific Railway Toronto Yard. But in 2020, pattern shifted. Higher pollutant area become more concentrated around the downtown core and highway network. So if we go to the next slide, okay, we have this non-uniform trend and spatial change in NO2 concentration over the entire city. And it was now it is very interesting for us to find out what happened to the environmental justice, because somewhere we have increased, somewhere we have decreased. For this analysis, we focused on the environmental justice at the dissemination area level, at the level, using the data from Ontario Marginalization Index for two census year, 2006 and 2020. So this figure show the relationship between NO2 concentration and different marginalization index group which groups this different marginalization index group into 5 categories. For example, if we look at to the chart bar chart, the blue one is 2006 and the orange one is 2020. The first category have the lowest marginalization index value, and the most right category have the highest value. In 2006, I mean the blue one, the bar chart, area with the high residential instability, let's say RI, and material deprivation, MD, and ethnic concentration, EC, had higher NO2 level compared to the area with lower level. Specifically, area with the highest RI, I mean that residential instability, had 20% higher NO2 concentration. The highest MD had 3.5 higher, and highest EC, I mean that the ethnic concentration had 5% higher. By 2020, the orange chart, if you look at the orange chart, although overall NO2 level decreased, the gap between area, however, the gap between the area with high and low RI, I mean that residential instability and ethnic concentration widened. The highest quantile for RI and EC had 87% and 12% higher NO2 concentration. That is a huge increase comparing to 2006. So in summary, we can say that NO2 decreased because of better traffic emission. But we doesn't have an impact, a positive impact on environmental justice indices. So if we go to the next slide, as a conclusion, this study showed the model does a good job for tracking the real world trend in air quality improvement. It also points out the improvement in NO2 level are not equal across the city. Some areas, especially those with the high residential mobility and diverse ethnic populations, still face more kind of pollutant. Even thought overall, the level has improved. Area with high residential instability and ethnic concentration continue to struggle with the pollutant, with higher pollution. So this highlight the need for more effort. Since low-income people and new immigrants living near the highways and more affected by NO2 pollutant, which show we have to look at better to the environmental justice, and we have to have better plan to improve this area. So thank you so much for your attention, and if you have questions, I'm happy to answer.
Great. Thank you very much, Arman. And now is a great time for questions, either in the chat or you can raise your hand and we can have a question aloud. Any questions from Arman? Well, maybe I'm always struck when we talk about environmental justice questions, where those who are maybe low income, higher material deprivation, etc., typically have greater exposure to negative externalities of transportation and all sorts of other things. And maybe that's the reason why they can afford to live in those places, because they're less desirable places to live.
Yeah, exactly.
If we remove those negative externalities on those populations, it makes them more desirable places to live in general. And will that is it an unsolvable problem? Does that mean that the prices in those locations will rise, and the people who have lower incomes might have to move elsewhere, where there again is those negative externalities where they can afford to live?
Honestly, I'm not 100% agree to remove that population, because those are a part of our community that need more help. And I know that there are some improvement in other locations, but still we have a lots of high-rise construction around the highways. I can see every year we have many highways that constructed around major road and highways, and those location are very kind of vulnerable to these higher pollutants. So if we look at from this viewpoint, that those are a part of our community that is and actually that a part of weak community that need more help, I think, and we can think about other techniques, other like methodology to improve the impact on this part of community. So whatever that this model gave us came from the traffic. Using this model, we can only include the impact of change in traffic all over the city, and we exclude the impact of regional impact of NO2 concentration. So it means that this study showed that the source of problem is traffic itself. We have a lots of traffic on highway, so we have to think about that. If we don't want to ignore these people, then we have to think to decrease this pollutant in a way. I don't know how, or if we can move the construction that is really very intensive around the highway to somewhere else to decrease this impact on this specific population.
Right.
That's what I'm thinking.
Sure. Thank you very much, Arman.
Thank you.
Anybody have any final questions before we wrap up? Seeing none, and I guess it's the end of the day. Thank you very much, Arman. Excellent
Thanks so much.
presentation and great food for thought. And now I'm going to pass the torch back to Karim, our organizer, event manager, and he'll be giving some closing remarks.
Thank you so much, Professor Matt. And thank you for joining us. I would like to thank you all for joining us today and yesterday. And I would like to thank you for your active participation throughout the symposium. We really appreciate the time and the insights each of you really brought to the discussion. And just as a follow-up very quickly, I want to highlight that we will be sharing the presentations and any related materials, including the recordings of the sessions for the 2 days, yesterday and today, via email. So please keep an eye out for those in the upcoming days. So once again, thank you for being here, and we look forward to continue the conversation on the topics really we covered in the last 2 days. And have a wonderful day, and see you next year.